Dear students, so welcome back to our NPTEL online certification course on analog electronic circuits. Myself Pradeep Mandal from EE and ECE department of IIT Kharagpur. Today we are going to continue amplifiers with active load. We have started this topic and today primarily we will be discussing about numerical examples. So, the plan for today it is numerical examples and inherent design guidelines. While we will be going through the numerical examples, we will also be giving hint towards how to design a circuit specifically for CE amplifier having active load and then common source amplifier having active load. So, this is BJT version and this is MOSFET version. So, let me directly come to the circuit. So, here we do have an example. Yesterday we have in the previous discussion we already have mentioned that instead of having a passive load, we like to use active load, and the purpose of this one we have discussed that to enhance the voltage gain. And here we do have the different parameters of the two transistors. For Q1 beta is 100, for Q2 beta is 200. Just for a change we are taking different value of beta, and VBE on of transistor 1 it is we are approximating it is 0.6, VEB it should be mod actually, VEB of transistor 2 also we are assuming 0.6. The early voltage of transistor 1 it is 100 volt. So, likewise let you consider early voltage for transistor 2 also 100 volt, and then the capacitances namely base to emitter C pi 1 for transistor 1 it is 10 picofarad, and likewise for transistor 2 it is 10 picofarad, and then on the other hand base to collector C mu it is 5 picofarad for both Q1 and Q2. Then also we do have the information about the supply voltage. So, here we consider this is 12 volt and the bias circuits informations are given here. So, RB1 we have taken 570 kilo ohm, and then RB2 it is 1.14 mega ohm, and we are assuming that in case if we have some load capacitance and its value it is given here 100 picofarad. So, you may have probably you might have observed that the value of the beta of the two transistors they are different, and then to make a balance of that the collector current of transistor 1 and collector current of transistor 2 they should be equal, and to do so to get that what we have done it is that the base current of transistor 1 and base current of transistor 2 we are making it different. In fact, it is just compensating that. So, to achieve that the value of this RB2 it is 2 times of RB1 just to compensate the beta difference. So, end of it what we are getting here it is collector current of transistor 1, assuming the device it is in active region of operation it is its beta multiplied by IB, and IB it is supply voltage minus VBE on of transistor 1 divided by RB1, and that is 100 multiplied by so this is 12, this is 0.6. So, that is 11.4, and then Rb it is 570 kilo. So, that gives us this part it is 20 microampere multiplied by 100. So, that gives us 2 milliampere. Now, on the other hand, if you see the transistor 2, its condition it is to find its collector current, it is equal to its own beta multiplied by the same supply voltage minus VEB, VCC minus VEB of transistor 2 divided by RB 2, and so this is beta is 200, and then we do have 11.4, again this part it is 0.6, and then in the denominator we do have RB 2, which is 1.14 mega ohm, 10 to the power 6. And again this part, though it is 10 microampere, but after multiplying with its own beta, so this is giving us 2 milliampere of current. So, the bias resistors, base bias resistors, it is such that they are compensating the beta difference, and finally, both IC1 and IC2 they are equal. Note that in this equation we have not considered the effect of early voltage. In fact, we should what we should do it is IC it is equal to beta times IB, and then we should multiply with 1 plus VCE divided by the corresponding early voltage. So, since this part beta into IB for both the transistors they are matched, then we should directly compare 1 plus VCE divided by VA of the two transistors equal, and that eventually gives the output DC voltage here. So, to get the DC voltage at the output node, say V out, what we can do? We can compare beta 1 IB 1 multiplied by 1 plus VCE of transistor 1 divided by VA of transistor 1 equals to beta IB of transistor 2 multiplied by 1 plus VEC of transistor 2 divided by VA of transistor 2. Now, this part and this part we have seen here they are equal. So, now just by equating this factor, what we can get here it is, since the early voltage of the two transistors they are equal. So, that gives us VCE 1 equals to VEC 2, and also we know that VCE 1 plus VEC 2 equals to VCC. So, this is VEC of transistor 2, this is VCE of transistor 1, that is VCC, which is 12 volt, and from that we can say that both of them are equal and they are equal to 6 volt. That gives us this output voltage equals to 6 volt, and hence we obtain the operating point of the two transistors, namely. So, let me summarize the operating point. So, we do have IC 1 equals to IC 2 equals to 2 milliampere, VCE 1 equals to VEC 2 equals to 6 volt, And so the other things we already have obtained, namely IB 1 equals to 20 microampere and then IB 2 equals to 10 microampere, right. So, since this is 6 volt and this is 0.6 volt, this is supply voltage is 12 volt, here the voltage it is 12 minus 0.6. So, that is 11.4 volt. So, that is the operating point. So, from that we can calculate the small signal parameters of the transistors, namely GM, say GM of transistor 1, it is IC divided by VT, thermal equivalent voltage, we can consider that is 26 millivolt. So, this is 2 milliampere divided by 26 millivolt. So, that is 1 by 13 mho. So, likewise GM 2 it is also equal to 1 by 13 mho. Then R pi 1 equals to beta of transistor 1 divided by GM of the transistor. So, that is equal to 100 multiplied by 13. So, that is equal to 1.3 kilo ohm. So, likewise you can also find that R pi 2, which is beta 200, and then GM 2 it is 1 by 13. So, that is equal to 2.6 K. Then R naught, we do have some space here. So, let me utilize this one, R naught of transistor 1, which is early voltage of transistor 1 divided by IC. So, this is 100 divided by 2 milli 10 power minus 3. So, that is equal to 50 kilo ohm. So, likewise you can also find that R O 2 equals to 50 kilo ohm, right. So, that is how we obtain the small signal parameters of both the transistors, and then we can try to find what will be the corresponding gain and so and so. But before that, it is also important to see that if the DC voltage here it is 6 volt, if the DC voltage here it is 6 volt, how much is the signal swing we can expect from positive from this equation point towards the positive side. The voltage at the collector it can go as close as the supply voltage. In fact, supply voltage minus VCE sat saturation, and we can assume that VCE sat of both the transistor are around say 0.3, VEC of transistor 2 and saturation it is equal to 0.3 volt. Typically, that is what it can be taken, sorry 0.3 volt, I mean 0.3 volt. So, the we do have a 6 volt DC here, and then if we consider this is 12 volt. So, total here it is 6 volt minus 0.3. So, the positive side I should say that output swing in the positive side it is 12 volt minus 6 volt DC minus 0.3. So, that is equal to 5.7 volt. So, likewise negative side we can say that here we do have 6 volt, it can go as low as in ground plus 0.3. So, you can say 6 minus again 0.3. So, that is equal to 5.7 volt. So, output swing wise you can say it is plus minus 5.7 volt, which means that the voltage here it can go as high as, with respect to 6 volt here, it can go as high as 11.7 volt. Likewise, lower side it can go as low as 0.3 volt. Okay. So, that is the good swing. Now, next thing is that how do we find the small signal gain and so and so. So, in the next slide what we can do, we are going to draw the small signal equivalent circuit, but to calculate the gain we need to remember these parameters, particularly small signal parameters values. So, you have to keep that in mind, and then we will be utilizing this parameter value in the calculation of small signal gain and so and so. So, in the so here we do have the circuit, it is for our reference, it is shown here, and the corresponding small signal equivalent circuit it is drawn at this place. So, for transistor 1 Q 1 we do have the small signal model drawn here. So, likewise for transistor 2 we do have the small signal model drawn here, and then we do have RB 1 here, RB 2 here, and this node it is AC ground. So, that is why it is connected to ground. And note that based on this VBE, we do have GM into VBE flowing here, and incidentally this node, the RB2 it is connected to ground, and the other side it is also connected to ground, and hence we can say that this VBE 2 equals to 0 volt. So, that gives this portion equals to 0. So, as a result we can ignore this part, and then you can find what will be the corresponding V out in terms of this input signal, say Vs. Now, since we are ignoring source resistance here, so we can say that VBE 1 incidentally equals to Vs, assuming that this capacitor it is successfully bypassing the signal to the base of transistor 1, and then we do have the current flow here GM 1 into VBE 1, and that is flowing through RO 2 as well as this RO 1. So, the corresponding V out equals to, since the current is flowing in this direction and the polarity of this voltage we are defining like this is positive. So, the V out it will be minus the current flow GM 1 into VBE 1, which is Vs, then multiplied by the equivalent resistance of this RO 1 and RO 2, which are actually in parallel connection. So, after making the supply node to connected to AC ground, these two resistances they are coming in parallel, and if you recall that okay, so this gives us the V out by Vs, that is the voltage gain AV, and its expression is GM 1 into RO 1 into RO 1 in parallel with RO 2. So, we can say that the voltage gain equals to GM 1 it is 1 by 13, and then RO 1 and RO 2 both are 50 K in parallel. So, they are giving us 25 K. So, this is 25 k divided by 13, and that is equal to something like 1900. I made I have done some calculation for you, 1923. So, this is the gain. Now, we can try to calculate the input resistance based on the information available, but let me clear the space. Yeah. So, input resistance on the other hand, it is R in equals to R pi 1 in parallel with R B 1, and you may recall that R pi 1 it is equal to 1.3 k, that is in parallel with 570 k. So, you may approximate that this is 1.3 kilo ohm. So, we obtain the voltage gain, we obtain the input resistance. So, next thing is, so these two are done, and next thing is that output resistance. So, to find the output resistance, what you have to do, we can stimulate this circuit by a signal called V x, and then we can observe the corresponding current here. If the current is I x, then you can say that the output resistance R o equals to V x divided by I x. So, that is the methodology we follow to find the port resistance, and while you are doing this exercise, we have to consider the other sources, signal sources are 0. So, we can say this is equal to 0. So, that makes V b also equals to 0. So, that makes this is also equals to 0, and this source anyway this is 0. We do have ground here, we do have ground here. So, the V b 2 same as the previous case, it is equal to 0. So, that gives this part also equals to 0. So, we do have, so we do not have this part, we do not have this part, only we do have R o 2 connected to ground here, and R o 1 it is also connected to ground here. In fact, directly you can say that this R out it is equal to R o 1 coming in parallel with R o 2, and both of them are 50 k. So, 50 k 250 k is in parallel, that gives us 25 kilo ohm. So, that is the output resistance. So, next thing is that the input capacitance. So, while you are talking about the input capacitance, we have to consider the C pi, and so this is C pi and then this is C mu. So, we do have C mu here and then we do have C pi here, and likewise here also we do have, but that is not really contributing anything towards the input capacitance. And you may recall that C in it is C pi as is, and then C mu of transistor 1 multiplied by 1 plus voltage gain magnitude of the circuit, and this one we already have calculated. It was 1900 around 23 or something we said. So, C pi it is 10 pico, and then C mu it is 5 pico multiplied by 1924. In fact, that gives us something like close to 1 nanofarad, close to 1 nanofarad. No, it is 5 sorry, close to 10 nanofarad. So, that is close to 9.63 nanofarad. I think I have done the calculation, yes. So, this is matching with that. Yeah. So, this is 9.63 nanofarad, and from this information 5.93 nanofarad, and then this okay. In case if we have some source resistance, then we can calculate the cutoff frequency coming from the Cin, but since in this exercise we are considering Rs source resistance equals to 0. So, its contribution to the cutoff frequency we are not seeing. Instead, the upper cutoff frequency it will be decided by the load capacitance here, and its value it is given here 100 picofarad, and the output resistance R O. So, the upper cutoff frequency equals to 1 by 2 pi into output resistance is 25 k, 25 into 10 to the power 3, and then we do have 100 picofarad, which is equal to 10 to the power minus 10. In fact, if you calculate this, this is coming 10 to the power 7 divided by 50 pi, and that is coming close to 63. So, that is 63.63 kilohertz. Okay. So, in summary, what we can say that the cutoff frequency it is getting reduced, gain got increased, and output resistance also got increased. Of course, the input capacitance also got increased. So, to summarize the performance of this CE amplifier with active load, probably we can see in the next slide, and then we can compare performance of CE amplifier having passive load. So, in the next slide we can see that. So, here we do have the table to write different parameters, namely, so we do have voltage gain. In case circuit load, CE amplifier load, if it is active load, voltage gain what we said is 1923. Let me use different color, otherwise it is not visible to you. 1923. Input resistance it remains same 1.3 kilo ohm. Output resistance it was 25, 50 and 50 in parallel, 25 kilo ohm. Then input capacitance it got increased 9.63 nanofarad, and 3 dB bandwidth. If I say that 3 dB bandwidth or upper cutoff frequency to be more precise. So, the upper cutoff frequency it was 63.63 kilohertz. Now, if I compare this performance matrices with the performance matrices of CE amplifier having passive load, and here we do have the corresponding circuit, and to keep the two circuits comparable, what we have done is that we have taken this RB and the corresponding beta, it is such that the collector current here it is 2 milliampere. So, the corresponding GM and R naught they are essentially same. In fact, early voltage we can consider also VA. For this case it is not so important, because we do have the passive load which is dominating, and the resistance of that passive load it is given 3 kilo ohm. So, R O of this transistor it is 50 kilo ohm, and the output resistance. So, that gives us output resistance of 3 kilo ohm in parallel with 50 kilo ohm. So, that is around 2.8 kilo ohm. So, the voltage gain it is GM1 or this GM multiplied by this RO. So, that is equals to 1 by 13 multiplied by 2.8 K. So, that is equal to 1218. I have done this calculation for you. So, yeah, so this is 218. On the other hand, input resistance, you may say that it is getting dominated by this R pi, which is same. So, this remains 1.3 K, and output resistance we already have said that 3 K coming in parallel with 50 K for early voltage of 100 volt with a collector current of 2 milliampere. So, this is output resistance is 2.8 K, and then C in of course, it depends on the voltage gain. So, since the gain here it is low, so it is expected that the C in is also lower, and we have done this calculation for the same value of this C pi and C mu, and that it comes 1.16 nanofarad, and the corresponding bandwidth or 3 dB bandwidth here, it was 562 kilohertz. Now, if you compare these two and try to see the difference, basic difference, the gain it is higher, so almost 10 times higher, and the resistance here it is higher, and also the bandwidth, if you see, this is also close to 10 times higher. In fact, now the bandwidth of the passive load corresponding to the circuit corresponding to passive load, it is higher. So, if you compare the frequency response for this active load and passive load as it was anticipated. So, if I say that the frequency response, particularly higher side, if you see, so gain it is very decent, and then it is having 3 dB bandwidth, and then for the active load on the other hand, the gain it got increased, but then the bandwidth got decreased, and the increase here from here to here, the increase here, whatever the factor we do have, that is primarily coming from this RO difference, and same RO difference it is also creating the same effect here. So, here it is getting increased. So, this factor it is basically the factor by which this gain got increased and the bandwidth got decreased, it is same, and which is defined by the RO difference. So, if I multiply this gain and then bandwidth, that remains same, and hence the gain bandwidth product it remains same. In my calculation, what I have done is that I simply multiplied this gain and this bandwidth, and it is coming close to 122 megahertz for both the cases. So, red one is with active load, and the dark one it is with passive load. So, that is the comparison of the two amplifiers. Okay, so, let me take a short break, and then I will come back for common source amplifier.